Well, happy International Women's Day indeed. Thank you, Greg. He's excited. We'll give everyone a few more seconds to settle in. And now it is 1 p.m. in New York. I'm based in New York City. Wherever you are, welcome to our webinar today. We'll talk about 3D printing or machining, and let's go through our agenda. To start with, Greg and I will introduce ourselves, and then we'll talk just a little bit about Sometry, just so you know where we got our expertise and experience. But we'll jump right in and give you an overview of CNC machining as well as 3D printing. But between the two, Greg will give you some really interesting insights about subtractive versus additive manufacturing and a trade-off of each. Then he's going to go through 3D design paradigm shifts, as he has over a decade experience, and he'll tell you a little bit more about it in a bit, about what has been introduced into the technology of material science and processing options. We'll also talk about cost drivers, because some of you might be engineers, but some of you might be supply chain folks who have to watch your P&L very closely, as well as optimizing your long tail spend maybe. Then we're going to do a recap and a Q&A at the end. But let's start with who we are. So, Greg, the international mystery man of man of mystery. Yes, over to you.
Thanks so much, Kathy. And hi, everybody. Thank you so much for joining today's webinar. We're really excited to talk about choosing between CNC and 3D printing. And this is something where I work in a lot. My professional career, I've worked for about 15 years in product development, additive manufacturing, and traditional methods. So I've been kind of spoiled and being able to be in a manufacturing agnostic environment where we look at projects, and a lot of my consultation with either the customers or internal team of experts has been on which process should I choose, why should I choose it, or what material, and even at this stage of my product development process, what's best for now and what should I be designing towards for later. So that's something that I do here as a director of application engineering at Xometry. And I'm just spoiled because I have such a great team of experts and industry leaders throughout not only Xometry, but throughout the industry that we work with and consult with regularly. And Kathy.
Thanks,
hello.
Greg. Hello. So happy International Women's Day. With my accent, I'm a bit of a weird person. So I grew up in Hong Kong, but built my career in London. But underlying everything I do is always about how can we use data technology and storytelling to bring communities together. My role at Xometry Thomas is to grow our community as well as the real manufacturing economy. And you're all here today. What we're going to do is we'll democratize what we learned through decades of working with manufacturers and engineers and give you all the highlight top tips. But also, Greg and I have, we are weird in a way that we love actually meeting all of you and be friends with you. On this webinar, there are already over 140 of you showing up today. We'd love if you could just, at any point, ask any questions using the GoToWebinar console, as well as chatting with us. Greg will be busy presenting, but
Absolutely.
I'll be his sidekick. Without further ado, we already talk a lot about us, Greg. Let's proceed to the next slide and find out more about you. So I'm launching a poll right now, and we love to just, you joined this webinar really about how should you pick between machining and 3D printing. Could you fill in the poll and let us know what are your manufacturing goals? You can select any of the options, all of the above, so that we can cater and design a webinar on the fly that's more suitable to your need. I'm going to give you guys like a minute. Yep, we got 20% voted. The number's quickly going up. Yep, almost halfway there. Over 50%. This is exciting. I'll show you guys the result after also. Just 10 more seconds for everyone.
It's great, over 70%.
Over 75 now.
Nice.
Perfect. So I'm going to show the results in 3, 2, 1. Very interesting, Greg. Look at this. So 70% are looking into rapid prototyping and low volume production, about 25% on high volume production, and 21% looking for a new supplier.
No, that's awesome to hear, and it's something that it's I always say, like, when you're with these technologies that we're talking about, you can serve a customer of one. So a production, an end-use production item can still be a low volume. I used to use an analogy when we talked about working in commercial flight, for instance. If you have one part and 100% of these commercial aircraft, you may still be making less than 500 pieces, but they absolutely need to be qualified. They absolutely need to hit the spec, and you need to check off all those boxes. And so it's depending on what you're looking for, we have a lot of different solutions, here at Xometry. And like I said, we are very manufacturing agnostic. Xometry offers about 20 different manufacturing processes. So when we're looking at different projects, we are able to think about not just what we have, because we have everything, but it's the strengths and trade-offs, what's going to bring the most project success. Some of the highlights here, obviously today, we only got an hour. We're going to be talking about CNC machining and 3D printing. We're narrowing down that scope. But we also have formative processes like sheet metal fabrication, injection molding, die casting, extrusion, as well as other ways to bridge that gap, whether it's laser and sheet cutting, urethane casting. We have expertise, and we have a tremendously valuable tool to help you get that sourced readily and on time. So let's just talk a little bit about Xometry. And I'm going to go through this pretty quickly because we have so much content to cover today. But I do want to give you context on where we are and what makes us a little bit different than just a direct manufacturer. Xometry is a digital manufacturing marketplace. We were founded in late 2013, really started making parts for our customers in 2014, and have grown and grown and grown and grown since then. And as a marketplace, we do work both with buyers, those people who need stuff made, as well as the suppliers, those who are able to create those parts, whether it's a tool and die company, a 3D printing company, machine shops. We have a platform that helps bridge that gap. We serve over 30,000 customers, and our global network, started domestically, but now we expanded globally, is over 10,000 suppliers. Adding to that, a little over a year ago, Xometry actually acquired and brought in Thomasnet, which I've been very excited about because it helps fulfill this goal that we have, where we want to be the first place you go to get something made. Because we have our direct offerings through Xometry's digital manufacturing marketplace, and we also have the Thomas listing, which adds, a little bit, maybe a few more suppliers, about 500,000 more, and over 76,000 manufacturing categories throughout that. So just we want to be a tremendous resource for you when it comes to manufacturing. And it's better to show than tell. So we do things a little bit different on our platform, having a technology-driven platform that helps aggregate the demand. So you as a customer can use our instant quoting engine, upload files, get instant quoting right away on parts over these variety of processes. It helps us automate and scale that RFQ process that may often take days for you to get responses for. You get instant results. And I'm going to show you a little bit of that right now, just kind of give a sneak preview. Again, I want to be sensitive to time because we just have so much to cover here. But I've moved, I've alt-tabbed here, so you probably see our instant quoting engine. I'm just checking to make sure you guys have that view. Good. And this is what you see on Xometry.com when you log in. So this is your personal dashboard. I'm logged in as myself, obviously, but you're able to upload and create your digital inventory. From your recent uploads or a new upload, you could quickly go and get a quote. And I'm doing this in real time. This is on our live site here. In this case, I've added a couple parts here. It's defaulted to what it thinks these may be designed for. So it's pretty close because one of these is, one of these is going to have more complexity. So it's looking at selective laser sintering, which is a good value of that complexity plus cost which is a 3D printing process. The CMC sample is going towards actually a 3D printing example because it could be either way. But you can see here, I can go and quickly say, hey, let's take a look at this price for CNC machining. So again, this is live on Xometry's website. I can click, change my process in a click of a button. I can move to a variety of materials. In fact, you could see just how many materials we have offered here. And if you don't see what you're looking for, you could just click other and write it in, and our team will be able to look at it, review, and update that quote. You can see pricing and lead time updates automatically as you are increasing your quantities and editing more features or finishes on your part. The same thing goes for, on this one here, if I'm looking to move this to for example, a 3D printed aluminum piece. So actually, I just printed out some of these pieces here recently. They came out fantastic, but you can see some of these features. And we're going to talk about why I can 3D print those in just a moment here. I can move very quickly to a process like metal 3D printing, direct metal laser sintering, aluminum. And you're going to see that price bump, but that's something you get that feedback right away with. So I really wanted to show you what that looks like when you are looking at Instant Quoting Engine, and what we really mean by automating the procurement process, becoming the digital manufacturing marketplaces. We're able to bridge that gap, get you very quick quotes. We use 3D, we use those 3D models to actually recognize features. And even as you set that project up, when you press buy, we use our vetted manufacturing network and use AI and machine learning to match make as well. So the heart of our platform is this AI and machine learning and deep learning tool that we have. I'm going to take a break because now it's time to actually talk about CNC machining and 3D printing. So we're going to go into bulk of this, and I really want to start with what we know, the stuff around us and these paradigms that we have, where you may not realize it or not, but you probably are. We probably are. Already have a paradigm in mind about what manufacturing is. But I'm reversing really quickly here because I did miss my slide here. When I'm looking between CNC machining and 3D printing, these are the kind of top reasons I may go one design direction or another. And it has to do with those requirements. So we have those hard R's, requirements, and we have those, those soft D's, desirements. So when you're looking at this, what's the requirement, what's the desirement as I'm producing my parts? A lot of these have to do with the physical nature. So surface finishes, tolerances, how tight do I need measurement features and repeatability on my project? Cost. That's something that's just huge and depends on the volume, the lead time, and other value factors to it. Materials availability is a big one. The size of those parts, especially when we start talking 3D printing, you may find some limitations as you move up to a larger scale. And then throughput. How many do you need now? How many do you need each year? That may be a very different conversation when we talk about the choices that we make between 3D printing and CNC machining. So now let's talk about paradigms. If you look in front of you, if you look at your keyboard keys, if you look at the parts that you have, metal pieces, parts of your desk, doorknobs, etc., they've probably all been produced in what I'm classifying as traditional manufacturing. Either that or very close tertiary to that. When we talk about traditional manufacturing, the base make usually starts with something larger and then reducing it down to a final shape. So you're starting with a net blank of some sort and reducing it to the shape of the final part you're using. For most common example that we're talking about and what we're going to discuss a lot today is CNC machining. So CNC machining, I have that net material and I'm removing it down using tools to reduce it to the final shape of my product. And the stuff we see around us, like these things that are into high volume production, my injection mold parts, these die cast metal pieces, they also fall in the same paradigm of subtractive because the tools that made those things are also CNC machined. What that means is we're kind of used to seeing certain aspects of CNC machining, and we may not even realize that that's our paradigm and that's our normal. That smooth surface finish from CNC machining comes from a end mill, a cutting tool, producing features of a part. So with a CNC machine, you are using a block of material. So say it's aluminum or raw material there. It is held inside this machine that can move that material around against a end mill, which is typically has a vertical movement in the 3-axis machine, but it can also have secondary movements as well to it. That end mill is almost like a drill bit, and it can be a drill, but it's usually, end mill has a flat feature to it. It's able to cut on the side as well as cut down into your part. So as it plunges into the part may be moving underneath it, creating features and pockets, so edges, pockets, other features on that part. And as it's cutting, it does leave a pretty smooth surface finish. So that typical is 125 microinches RA. And when you look around the parts, behind me to my right here, the CNC machine parts, it's something we expect because it's something that we know. It's our paradigm of what a typical manufactured part looks like because it's been tried and true for such a long time. There are design considerations. When I am cutting with a round tool, it's very hard to make square internal corners and features because that tool cannot all of a sudden just kind of cut that out. You need to add specialized tooling or secondary operations to produce that. And also that round tool profile, that kind of drill-like profile that's making, can't move around corners. It can't twist at the end, for example. So other than basic undercuts and undercutting tools, it's very limited in how to manufacture things that may have more organic, especially with internal features or features such as a lattice, for instance. The highest cost drivers for CNC machining tend to be that talent. The talent for machining is in the person. You can make a old CNC machine do very magical things if you have the right talent behind it. So the machinist has their own overhead. They need to produce setups, programming, and operations to produce different sides and features of a part, and all that adds to the cost. So even at quantity 1, you need to do all those operations in order to produce that first unit, and that will actually drive into the cost of that part. Machine overhead is another large cost driver. When we talk about CNC machining, these machines typically are in around the 100,000 to multiple hundreds of thousands range, depending on the type of machine that you're using for industrial manufacturing. And that's amortized into the cost of the part. You're renting that time when you're producing those features on those parts, operation to operation. The more complex the machines, the higher the overhead too. So the more complex the part often drives higher overhead machines, such as a 5th-axis machine, which may be able to cut more angles of the face, reducing operations, but again, increasing overhead on that part. And ultimately, CNC machining does have secondary processes to it. So if you do need to add a finish like an anodize, a plating, chem film, powder coat, all that can add incremental costs as well. But like I said, it's what we know. CNC machining is pretty awesome. It is a tool that is highly versatile because we have gone to college about it. We have learned through generations and generations of practical knowledge and documentation, metallurgy, qualifications, ASTM standards around these materials and the processes used to make these machine components. Also, I can do some things with the machine that are really cool, like I could stop and slow down and measure. So I could do in-process incremental changes to hit, for example, very, very tight tolerances on my part against a technical print or requirement. But that characterization of materials is just so important because for me, when I'm working on a machine part in industry, I don't even think twice about buying a certain material like 6061 from dozens of vendors because we know that material has been so tried and true that as long as you are, as long as you're buying from a reputable vendor, you're going to get the same results every single time. So as an engineer, you may be just assuming the mechanical properties within that material, and then you're designing your shape around that, where it can be a little bit different with other manufacturing processes. But that established track record, just works really, really well in machining's favor, and it brings that consistency, reliability, and predictability that is very critical for a lot of industries. And turnaround can be pretty quick. As a service, we usually start about 3 to 4 business days on smaller parts. If you're running internal, obviously you can push a little bit further. And then the more complex the part, the more finishes, the higher throughput needs, you see that movement into lead times into the weeks or so. But if I'm a company like Phase 4 Aerospace, CNC machining may be exactly what I need. If I'm building micropropulsion units, parts that are designed for space flight, you really need to have a high level of confidence and predictability on the outcomes you have. There is no let's bring it to the repair later moment when you launch something into space. And this is exactly why a company like Phase 4 may have a hard R requirement for machine components throughout their design. So in this case, they were working on a new electrical propulsion system. They chose Xometry because we were able to manufacture these parts to their specifications, including building a documentation chain from the traceability of that material all the way up to the manufacture and finishing of that material. We are also, as a Xometry, we are ISO 9001 as well as AS 9100 certified for aerospace manufacturing, and we're able to extend that throughout our network to hit those requirements, as well as any security or certification needs. But we help them cut their manufacturing costs by becoming a consolidated supply chain for these components, and hit all these specific needs that a company that may be in high-end aerospace, especially when they're doing a product launch where they need to move industry fast. So this new space industry just needs to keep on moving, keep on developing, and keep on pushing the limits. Machining helps take some of that guesswork away. Now, switching that around, machining is what we know. We have this idea of what a machine part looks like, it should look like, and this idea of workmanship throughout it. But 3D printing is a little bit different. 3D printing or additive manufacturing is this process of growing parts. It's typically a layer by layer basis, and you're joining materials together, either fusing them with heat or a chemical reaction, or sometimes a secondary fusion process. And it's doing this all dictated based on a 3D CAD model. So unlike subtractive, where you're starting off with a chunk of stuff and reducing it down to the final shape, 3D printing starting with an amorphous material, a filament or powder or liquid, and it is fusing or curing it into the final shape, kind of growing from the bottom to the top. So it has a much more organic approach to manufacturing. I just like putting a bunch of synonyms down here. I will say nowadays, mostly additive manufacturing and 3D printing are what we're using in the industry though. But additive manufacturing is a landscape. It's not just one machine doing it all. We have different ways of making 3D printed parts, as well as we have different outcomes, so different material classes. Xometry offers 8 unique additive manufacturing technologies and counting, including ways to make thermoplastic parts. So when I think thermoplastic, think about what you get out of injection molded materials, so nylons, ABSs, polycarbonates. We're able to print directly in those materials. So our top picks are going to be selective laser sintering and multi-jet fusion for their high versatility. FDM, fused deposition modeling, that's the one that uses that real filament of material to produce parts. It's very good for those boutique builds. I need a green ABS part, or I need a white polycarbonate part, or a black Ultem part. It has you're able to just specifically say that's what I need and print in that. We also have engineered thermosets, so these photopolymers that are liquid based. Three technologies offered through here. So stereolithography, which is one of the oldest 3D printing methods. So that was invented in the mid 80s, and it's just developed and really skyrocketed from there. And by the way, we're seeing a photopolymer revolution right now in the industry, which is really exciting. But stereolithography is great for smoother parts, higher detailed featured parts. Carbon digital light synthesis for a small part production, and then PolyJet for super vibrant and colorful concept models is a great go-to, as well as rubber-like simulations. Metal 3D printing, we have a couple options like direct metal laser sintering and binder jet metal. They are very different on how they're producing. Ultimately, you get metal parts. Binder jet has some secondary post-furnace processes. So it starts with a green shape that is held together with a glue binder, and then it has a secondary process where the part may shrink and move around a little bit, but it gives you more of a more of an option for like higher volume production than DMLS, where the parts are typically sintered to a build plate. And all these processes are industrial. So industrial 3D printing is something that is designed to work in environments such as what we're doing with the service. We're always running these machines. They're always cranking out parts. And they need to be very reliable and very repeatable for someone like you, who could be a customer, where you're ordering a part today, and then say you want to order 30 or 300 3 months from now, you're going to have that high level of repeatability. Hey.
Hey, David asked a really good question. We're just chatting on the side. Greg, can you mix and match the 3D printing processes, or they're all separate?
Yeah, that's a great question. So these processes act independently. So they almost have a vertical in how they're actually manufacturing the parts. So the base nature of how these parts are being created, it comes from the machine up. You can do things like multi-material 3D printing within PolyJet, for example, where you're mixing colors or different material properties in a matrix. So you could get kind of a simulated overmold or something like that. But for example, if I'm doing a SLS nylon 3D print and I want to have some aluminum on that, that would be a post-assembly operation. You wouldn't necessarily have the capability to mix both of those together. And there's a lot of reasons why. There's just a lot of reasons why we have dissimilar materials, science, the bonding, the heat and thermal properties of it, the machine characteristics can become very, very tricky there. So that being said, though, when we're talking about the benefits of 3D printing, it really just wins the low volume game. It's such a powerful tool for rapid prototyping and low volume production, because that talent, we talked about CNC machining, that talent is in the operator. With 3D printing, the talent is a lot of it's in the machine. And what I mean is we have some really talented staff that are doing build setups and programming and that digital setup for 3D printers. But they're able to do that and scale up to dozens of machines per operator. So you could have a small nucleus of talent able to produce a lot of parts, thousands of parts per month, with build setups and this digital programming. So it makes it very quick to add a digital file. Your build setup program is doing a lot of work for you and translating that information to the 3D printer, where the 3D printer is going to do its best to reproduce that shape using the process and its parameters. You could have one-day turns with 3D printing, even on a service level. It's not uncommon for us to get an order and build it overnight, ship it out the next day. Even some of the more complex parts, can only take a few business days to produce out. And what's really great about this and what's really unique about 3D printing is this function orientation. So CNC machining, if I have to pay for that spindle to turn around and mill out parts, I may be designing in a way just to reduce the amount of time that's working. So if I have a bracket, I may leave it quasi over-engineered. If I just need these functional features here, I'm only going to reduce the material there and leave the rest in a block shape. With 3D printing, the work's only when it's depositing material. So I could put that part on a diet and instead talk about function first in my design. So design what needs to be there, and then fill in the gap with what's required to keep it functional. And that you have dramatically different parts that come out of a 3D print design versus a CNC design, especially if you're starting from the bottom up in your product development process. And again, because it is building parts with a 3D model, it is one of the lowest barrier to entries for manufacturing, because it's just 3D model direct input for manufacturing. All right, got another question.
Right, we got a rapid fire round. We got three amazing questions.
Okay, let's go.
Kristen, what is the final density of DMLS and metal binder jet produced parts?
Yeah, so density-wise, DMLS it's so funny because industry, all of us say DMLS, but it's actually selective laser melting or other things, because sintering is injustice. You do have 100% dense parts when you're producing parts with DMLS. The weird zone is typically the outer quarter millimeter, and that's because of laser parameters and other things. And they can be tuned out a little bit. It's very design dependent. But DMLS, typically we look at it as 100% dense. As in, if I take a CNC mill and cut through my DMLS part, it's going to look like solid billet material. Binder jet metal has about 98% density, even with our single alloy materials. But that being said, it's very different than if I say 98% density on a casting, where castings may have visible voids in them in certain cases. The 98% density is homogeneous on a binder jet metal. So I may not make it into a pressure vessel, but what's good about that is your mechanical properties are still very predictable as an outcome. So you're not like worrying about a little void or a little dot that's going to mess up your properties. It is a homogeneous density to it.
David, what about making a part with one 3D printing technique, then put the result into another 3D printing process?
So certain processes, the shorter answer is probably or possibly, but there's a lot of longer answers in the development, the testing, and the scrap rate around that. So deposition processes where you are depositing a material like fused deposition modeling, or even something like directed energy deposition for metals, you can technically build on a substrate, right? So just like we're building on a build plate in most 3D prints from start, if you're going that route, you may be able to do you could build on top of an already existing part. But my screen should just be flashing asterisks there, because I will tell you, I have my geek hat on, but I also have my service hat on, which is what is reasonable to give you predictable results in a timely manner without doing research and development on your parts. And that's a very different story for reliability in industrial manufacturing. Yeah.
Yep. And I know we have a lot of questions pouring in. I'm going to let you keep going, but I'll just say one thing. Quite a few of you asked about the nature of Xometry as a marketplace, whether or not we make our own parts or we have our partners making our parts as a marketplace. Greg, can you answer this question that I think about 3 people already asked about, and then we can move on, and then I can queue up more questions in a bit.
No, absolutely. In Xometry, we do have expertise in manufacturing in-house as well as throughout our global network. By far, the vast majority of parts are done with our vetted partner and supplier network. And we rate them just as much, the same as we rate our internal capacity. So we do have some polymer 3D printing capacity and a nice little factory out closer to where I am in the Gaithersburg, Maryland area. And a lot of our team comes from actually running our own facilities in the past, our own machine shops, molding services, tool and die services. So what's really great about Xometry as far as our staff goes is, we love this business. We are just so incredibly passionate about what we do and the parts that we make. And we're also able to work with our suppliers. They have their own vetting processes. We have partner success score and feedback, and we also want to have stake in the game with them. So if there's anything where we need a strategic approach to producing those parts or working through our troubleshooting, our team's first in line to help with outcomes and success there. And speaking of that, I have this case study kind of showing where additive manufacturing plays like a really nice role. Dixon Valve, which they make a lot of parts that are actually traditionally investment cast or die cast as part of their business, but they also need to set up and do secondary operations on those parts. These parts are heavy metal. They take a beating, and they needed a fixture that can do the same. That work holding fixture though had some complexity to it that would be prohibitively expensive and timely to do with traditional machining. They found that direct metal laser sintering, so metal 3D printing, worked really well for this application. And it's kind of interesting because you see this is a direct metal laser sintered part here, so that kind of matte finish from the DMLS process. And it's actually holding on to a cast part. So this would be a traditional investment cast part here. I also love this application or this picture that they sent us about the jig and the fixture and process, because on their fixture is also something that they printed with their in-house printers, a plastic 3D print. So it's kind of 3D printing holding 3D printing, which kind of segues into, how do I mix them together? Sometimes you can be pretty clever about that, but this is a great application of how I have something that serves a very specific and very important need. I may not have 1,000 customers for this, but I need it to work and be functional, and 3D printing hit the bill. So I'm going to drive a little bit more into 3D printing, and I know some questions are coming in, and I think actually this may help out a lot too as we're talking about design paradigms, because it is a little bit interesting. And I dive into 3D printing more than I do with CNC for this session, because it's not what we know sometimes. It's something that we're learning about, and I want to spend time talking about these different paradigms that you have. The first off is growing. When I say manufacturing, when I talk about manufacturing and 3D printing, I say grow. We're going to grow this part. And that's because that's what it really looks like when it's being built. It's starting from the bottom, moving up to the top on a layer by layer basis, and you're producing those parts. It also means there's little nuances that happen on a part. For example, this piece here where you have a horizontal hole, that hole may have a little bit of a different look than a drilled hole because of the layers of that part. So when we start thinking about growing, all of a sudden in our design process, we also may be thinking about orientation as part of that, as part of our mental flow in designing. The other thing that's super, super important when we talk about CNC machining versus 3D printing is that 3D printers make net shapes. The tolerances, so scale and offset, is actually applied on the machine level. So this material on this machine with this parameter set will give you this type of result. So when we talk about tolerances, it's going to be usually at that plus or minus range, so plus or minus 5,000, plus or minus 10 thousandths, or 12 thousandths per inch, whichever is greater, is what you'll see a lot when you look at Xometry's online manufacturing standards. And that's because those printers unlike CNC machine, they're not able to slow down and stop and hit a critical data or feature. A lot of times it's an iterative process of building. Again, it'll be very close and it may work the first time around, but sometimes when you're tuning for production, you may do a scale, like do an offset or something in the CAD to compensate for a critical feature as your design. So you may have more of an iterative approach in design. And the last thing in 3D printing is 3D printing. It isn't building from a block, right? Don't have something clamped into place and then you're removing material. So when you're building from the bottom up, if you do have any features that are overhanging, you need to compensate for basically the existence of gravity. In this case, if you have something that's building like a T and you have those features coming out parallel to the build plate, so the top of the T there, you're going to need to build something sacrificial going up, so the support structures to produce a platform to put those parts on. And so the features need a support structure to actually create those features without them sagging or drooping in that area. We do remove those support structures as part of our normal practice, but it's really important to understand that with certain processes, the supports may be removed. In this case, you can see kind of the stippling here with a carbon DLS epoxy part here, but you may see remnants of supporting structure. And if you have critical tolerances or surface finish callouts on that, it's going to be rougher. So going back to this designing for growing, designing from the bottom top, you may start thinking about the process in which you're designing for, as well as orientation, and you want to put your critical features on the features that will grow naturally, so they will do that. They would not require supports to grow in that area. And I say that trying to mitigate any secondary operations like post-machining, for example. So we've talked a little bit about these paradigms, and as I said, CNC machining is kind of not necessarily one size fits all, but one process fits many. With additive manufacturing, you have these multiple processes. So how do I choose? I want to spend a minute or two talking about platform selection here, because the first question that I always have for a customer is, what is your goal? And this can change depending on where you are in your product development life cycle. So, if you're looking for the next couple of weeks, maybe it's prototyping, like a concept model, like I need to hit aesthetic goal or a prototype. Very quickly, we can start down selecting process that can work for you. So could it be low cost? Can it be fast? How can it achieve your goals? And you may look at, if I just want shape really quickly, that's going to be hit 90% of my needs. FDM, SLS, MJF, like those major technologies may just be perfect for you. But let's say you're moving towards something that needs finer detail or clear or more of a smooth surface finish. That's where you find stereolithography. These liquid resin processes tend to work really well. So I have a picture here of a part where you can print parts that are clear, or I'll say ice cube clear with our quick clear finish. But here's an example of something where I'm printing a part. It has a cosmetic need. It needs to be clear. And this is an auto-coatable feature. So this is SLA Accurate Clear View with a quick clear finish. But that's one outcome, right, for a prototype or a concept bringing me to the next phase of my product development cycle. Now, say you're looking for something that's end use. It's going to be installed. I'm going to use it, and I hope to forget about it. I hope it just works, and that's it, right? That's where we start looking at functional parts. And this could also be used as a surrogate for testing as you're bridging into production. But we have many options under this functional brand. So with metals, it's a quick down select with only a couple options. Non-metals, we have many more options available for additive manufacturing. So my next down select may be, if it is a metal, and is it a rubber-like material. We do have 3 3D printing processes that can produce rubber-like materials, including thermoplastic urethane from MJF, which is very popular. DLS has a TPU and a silicone-based urethane, and then PolyJet can simulate durometer, so kind of squish-like features within its technology on demand. If I have more demanding environmental requirements, I may be looking at some of these thermoplastics. So impact resistance, we have a lot of materials, including nylons, that are very good for impact resistant designs, especially if you look at like a material like nylon 11. Has a much higher ductility than a lot of stiffer materials like polycarbonate, and works very well there. In this case, I have a picture of Ultem 9085, which hits heat deflection and actually a lot of chemical resistance. It's a very high-end thermoplastic that you could directly print in. And some of our other questions may be chemical resistance or sterilization, but we can help narrow down our process and sometimes a direct material with this type of decision tree. The last thing, if you're choosing between CNC and 3D printing, the size of your design can play a huge role. If you're trying to make a car hood, we may either need to split and bond, or we may look at other processes in order to produce and fabricate that. Fused deposition modeling can print up to 36 inches with our current offerings. And we do have some abilities to print larger, but from a instant quoting standpoint, that's what we have there. So we have a 36 by 24 inch by 36 inch build platform in our Fortis 900 FDM machines. But you see that the smaller you get, the more options are available. So basically below 13 inches or so, you have a lot more optionality. Then once you get above that, you're going to reduce the types of 3D printing available. Potentially that reduces the material selection, and when the larger you get, the more coarse you may find some of your feature sets as well. So it's just something to consider, and this is a lot to take in, but I wanted to kind of give you a glimpse into some of these tech choices that we may be making when we're choosing our different additive manufacturing platforms. And pictures are always nice here, so I want to show that layer lines that you see with a fused deposition model. So that is that filament. So a filament-based 3D printing method gives you that filament-like finish to it. Liquid-based 3D printing, so resin-based like stereolithography, gives you a smoother finish. And then powder bed 3D printing processes where the base material is a powder, you have more of a powder or sugar cube-like finish. So unlike CNC machining where you're removing down, because you're adding up, the surface finish reflects essentially that base material without secondary processing. In contrast, this is a chemical vapor smooth finish of the exact same model. They're just kind of joined together here. And you can see that we can have add secondary processes to smooth out parts. With metals, both metal objects that we have here, these processes do produce in powder beds. So you see that matte finish compared to a CNC machine part. This is one's red anodized. You can see those kind of crisper, cleaner features from a tool moving through. You also see those rounded internal corners that are required for the design here. Something to note is, if you're choosing between, if you have a part like this that has organic curvature, that may have a lot of coring and material removed for it, or even inaccessible features like kind of this undercut area right here, which you couldn't actually access with a traditional tool, that's going to drive me more towards a 3D printing method for a lot of reasons, including cost reduction. If I was trying to machine this or to my best of my capabilities, it's going to add a lot of expense due to higher machine rate, a lot of detail, a lot of surfacing, adding hundreds and hundreds and hundreds of dollars on top of a part just for that curvature. And that's when it comes in comparing cost drivers. So this is kind of like our last big section here when we're talking about these choosing between processes, but sometimes it just comes down to cost. What makes the most sense for my product development? My total estimated volume for this, what's going to save me the most money or bring me to the level of sustainment that I need. Typically, CNC machining is going to win out with large, bulky geometries because bulk is less work with CNC machining. So if I'm machining and I have, I'm only taking out a few holes for one pocket, the rest remains that bulk shape. It is less work than a 3D printing design that has the same amount of bulk. We don't like printing bricks, and it'll add cost because every single piece of volume there is work for the 3D printer, where with machining, what you're subtracting is the work. So there's a very different paradigm there. And with that being said, when you're coring or lightweighting features, it is the opposite, right? So the more intricate, the more cored, lattice structures, for instance, work really well in 3D printing. They may not even be manufacturable with traditional machining. And if they are, it drives up costs significantly. Off-angle holes and organic features also play this role where if you have a lot of curvature on a machined part or off-angle features, you may either be adding axes to the requirements of the machine. So do I need, instead of a 3-axis, a 4th or 5th axis machine, or live tooling lathe or a Swiss machine to produce those components? With 3D printing, it is much more natural and much more akin to building organic and complex geometries. That could even be all of one geometry. So where you're combining assembled features together in one part can be a huge advantage to 3D printing. That being said, because you are 3D printing with near net shapes, precision and tight tolerances, the more count you have, the more call-outs you have, the more it may make sense to stick with a traditional manufacturing process because you can slow down and get those tolerances within that operation. When, say, for example, I was working with that previous example of that impeller or that propeller, and I needed to do secondary operations to it, at some point it may make sense just to machine the whole thing. So if you're able to work with with a near net shape and hit that complexity, 3D printing really wins out in those factors. Smoothness, that net shape, that 3D printing method, you see that powder-like finish we showed. You see that filament-like finish that we see. If you acquire a gloss finish like this, it's either going to be secondary processing with 3D printing, which can add expense, or it may just make sense to move to a traditional manufacturing method like machining or turning to produce that, because it's inherent in the process of cutting. And last but not least, deep pockets and channels. If you ever look at like these beautiful additive manufactured conformal cooled tool designs for injection mold inserts, they have this ability to add curvature and channels within. Or if you have a very deep pocket, especially something like this where it's a deep pocket and a hex shape, you may not even have the tooling to produce that feature, or require a lot of specialized requirements, including wire EDM, which could dramatically raise costs. 3D printing, it's cheap because it just doesn't print there. You know, it's just making the rest of the part. So it's in a lot of ways when you're doing this coring or this material removals, it's a cost reduction technique for 3D printing. And just kind of sealing this up here, when you are talking about costs, I did run this through our instant quoting engine. This is a little bit further back, but just kind of showing you a part that's kind of increasing in complexity. Moving through with machining, you're starting with just essentially overhead to just mill and plane the faces of the 6 faces of this part here. But when you're printing bricks, you're paying for that material, you're paying for that work to occur. As you start removing material, you start seeing the 3D printing methods getting less and less expensive, including this one where it's just shelled and cored. You can see that dramatic price drop right there because it's less work, right, to produce those. But you're adding complexity if you're removing material. So in this case, you could see as the complexity rises in the design, pricing will rise on the CNC component. CNC machining probably could not make this design here, but just for the heck of it, I put a price in, but there'd be a lot of DFM callouts on our site and from our team if you actually try to make this machinable. But you can see how just dramatically lowers pricing in a complex part because again, volume is a huge factor in versus complexity in pricing of additive manufactured components. Yeah.
We can recap, but we can also do another rapid round because honestly, guys, you're amazing. We have 165 of you. This is the best list of questions I've seen in all the webinars we ran. Actually, Wesley and Joshua, you guys should be friends. You're asking similar questions. How reliable is the metal 3D printing technology for industrial part production these days? Repeatability as a cost is a key driver for any production process from Joshua. How cost effective is an integrated 3D and CNC production process versus CNC alone? So they're both really kind of questioning the reliability of 3D or blended processes.
Yeah, absolutely. And this also goes back to what the type of processes for marketing, because we do hit the industrial level. So there's a lot of ways to make a metal part an additive. We're focusing on 2 main categories, that DMLS and that metal binder jetting. This is also an excellent segue in where metal 3D printing may work in your design and selection and even exchanging sometimes on inventory items. So it is reliable. It is, I mean, this is real metal. It's real metal material, and it is it's as tough as a billet. So usually, like when you're looking at scale of billet versus casting, a DMLS will be right below billet, but usually has properties above casting, and it also has some benefits above casting, cast components. Like I said, for porosity and other things that may be invisible defects within that process. DMLS does not necessarily have those considerations. I actually have seen a lot of direct substitutions in my career of something that may have a low volume required cast, so I only need a dozen of them a year, and it made more sense and was more reliable to move to a direct manufacturing approach using metal additive manufacturing. But the other things you could do, right? You could combine features, so you could build more complex pieces of your metal with metal additive manufacturing than you could traditionally, and still keep costs relatively low compared to doing that the traditional way. That low volume need, it doesn't scale well. So if I'm start looking into the hundreds or more, that's when I start. I would give you be the first one to give you a sanity check on saying, let's talk about die casting or CNC machining, or we have other choices to help your project be more successful and also be more valuable to you when it comes down to the costs. Polymer 3D printing. That being said, it's still something that you'll use regularly in your product development process, so it still wins those one-offs. Smaller pieces can scale into the thousands and still be competitive with molding. So that's usually parts that are about smaller than like 2 fingers together, give or take. And we have a lot of options there to help move up, but that's going to be in the polymer base. The other thing between DMLS and plastic 3D printing, or metal and plastic 3D printing, is that if your rev changes, cool, we'll just put the new rev in the next build. So you're not as dictated by your tool that's already established versus traditional processes. That being said, if we think back to the phase 4 example there, sometimes you just need tight tolerances. You need that surface finish. You need those critical requirements. You need that tried and true material. And that's a lot of industry. Don't get me wrong. Additive's going to get there and be just like what you think when you buy 6061 from McMaster. You just expect it to be 6061. But CNC machining does have a huge advantage where we just have this huge legacy of process, education, and resources around it, including quality inspection. So that qualification just really holds CNC to a very high bar that additive is working its way towards. With my last case study, we are I do want to highlight BMW because I think they do just a fantastic job of combining both where CNC adds value as well as where 3D printing adds value in their tooling, jigs, and fixtures. So we make a lot of jigs for their manufacturing plants at BMW. These are typically lower volume, so no more than dozens usually, and it's used along the assembly line. They're using 3D printing for large conformal pieces that can be lightweighted by reducing the infill or creating chord features for handheld jigs and fixtures. That helps reduce fatigue and reduces scrap rate. That being said, they're using CNC machining in traditional processes where they have extremely tight tolerance needs, because what they're using these fixtures for is installing components of that vehicle. Every single installation of that decal or that trim or that panel should be exactly the same place on every single vehicle. So a lot of times you see the components that are actually indicating on those features of the vehicle will actually be CNC machined. So sometimes machined plastic like Delrin, sometimes machined metals like aluminum 6061. And I even see that I love their parts because they color code them. So you see really fun anodized colors with a lot of these BMW parts. And then the main body may be 3D printed, again, to give you that structure, give you that organic conformal shape to hit the edge of the vehicles and actually really conform to the vehicle, as well as just to make it lighter weight. So I really do love seeing a mixture in our orders, and that's something that we have a superpower at Xometry, is using our quoting engine to just add your bill of materials and press buy. So with that being said, get some more questions ready. I'm going to jump into this because I know we are running low on time here, but we really do bridge product development and production with 3D printing, so it's across the whole gamut of the process. So quick reminder, we do have this wonderful instant quoting engine. All these materials, processes, selections are available just right at your fingertips. It's free to use. We even have add-ins for SolidWorks, Fusion 360, Inventor, and Onshape. So while you're in the design stage, you can actually use some of those tools that you can find on Xometry's website to really bring your design to the next level and get some cost comparison right up front. Xometry's resources are also really good. We have more webinars like this. So how to design for 3D printing was one of the most fun webinars I did. I got to geek out with some of my other additive experts. We also have downloadable design guides, case studies, and also the resources page is going to be where you're going to be able to find a lot of our CAD add-ins as well. So with that, happy to take on some more questions. And yeah, thank you all so much.
And thank you, Greg. And also, this is our first experimental webinar format. If you like it, when you exit the survey, when you exit the webinar, there's going to be a survey. We're thinking about maybe we do a manufacturing monthly so that we can invite all of you back again There are about 15 questions we got. We didn't have time to answer all of them. We can make it interactive. Now, I just wanted to say, Michael is actually one of our supplier, and he said, I might disagree on some of the points. We love challenging point of views. As a partner, we have supplied very tight tolerance BMLF parts with smooth finish. I just want to bring it up, and we're always learning from all of you. And also, Robert actually asked if we have experience in medical device validation and what it takes to transition to new style of manufacturing parts. I'm also going to jump right in. We have a dedicated team of medical device manufacturing operational folks. And you may not know, but for orders over $30,000, you automatically actually get a dedicated team of engineers, DFM experts, and your order will actually get pass on to our expert teams, and they will handpick the suppliers that we know that are extreme experts in the field. And Greg, do you have anything to add to that as well?
I think it's important to note that Xometry is our qualifications include ISO 13485, which is the standard for medical device manufacturing. We do aerospace defense parts. We're also AS9100, and within that is ISO 9001. So we're continually meeting the certifications and requirements for the industries that we have, like TS for automotive, and working on environmental and other certifications. I cannot understate the expertise and the talent of the teams that we work with every day here within Xometry, and as well as honestly the suppliers extended through. And in fact, we talked about that supplier that mentioned about DMLS and tight tolerances. Absolutely, I am talking near net shape, kind of as built finish. For the sake of this webinar, but secondary processing and machining and milling is very common, especially say, for example, using a cast surrogate, moving to a porting hole or something like that. It doesn't make sense to print those features. We're going to machine them out.
Right. I know we're at time, so unfortunately we can't in the moment answer other questions, but we captured all of them. So we'll follow up with you with our team, and please feel free to connect with Greg and I. You have the email on the screen. You can connect with us on LinkedIn. We are kind of genuinely super friendly, and we love just learning from you all and connecting and sharing information. So again, amazing turnout, really great interaction. All the positive feedback or even critical feedback is what keep us going. So thank you very much.
As Kathy said, thank you so much for your time. We love this subject. We love making parts. I also, want to say, try us out. We have a code right here, TryWeb25. Please feel free to use that. Try out some parts. Try a process you haven't used before. Just get your hands on. A lot of times, it's just fantastic, especially with the cost of additive being low. It's a show and tell moment. So give that a go, and thank you all so much again.
Thank you. Have a great day, everyone. And remember to exit survey. Thank you.
Cheers.